Question number 1. For the scalar field u is equal to x square by 2 plus y square by 3, the magnitude of the gradient at the point 1, 3 is. Now the gradient of the scalar field is basically del u, which is nothing but dou u by dou x I plus dou u by dou y j. So this will be 2x by 2 I plus 2y by 3 j. At the given point 1, 3, grad u is equal to, which we can also denote as del u, is x is 1, so you get I plus 2y. 2y is 6 by 3, that is nothing but 2j. What we need is the magnitude of this. So this will be square root of 1 square plus 2 squared, which is root 5. So the correct option for this problem is C. Question number 2. If z is equal to xy log of xy, then which of these following options is valid? This is a plain or a straightforward problem on partial derivatives, but a student with insufficient practice may get tempted towards using the Euler's theorem. All of us know there is a well-known theorem for homogeneous functions. Here, this function is not homogeneous in x and y because of this logarithmic term. So because it's not homogeneous, option A is ruled out. So we'll just see which of these remaining 3 will be valid. So basically you can see that you will have to estimate zx and zy. Zx is nothing but keeping y constant, x into the derivative of this with respect to x is nothing but 1 by xy into y plus log of xy. So we are applying a UV rule for x and log of xy. So you will get y into 1 plus log of xy. Let's calculate zy. This time x is constant. You apply UV rule for these two. So y into 1 by xy into x plus log of xy. So this is nothing but x into 1 plus log of xy. Now observe zx and zy. The bracketed portion is common. So here we have y, here it is x. So if you multiply this with x and this with y, then the outputs become same. Therefore, x zx will be equal to y zy. So x times this and y times this will produce the same answer. So option C for this problem is correct. Question number 3. The magnitude of the gradient for the function f of xyz is equal to x square plus 3y squared plus z cube at the point 1, 1, 1 is. So grad f, also written as del f, is equal to dou f by dou x into I plus dou f by dou y into j plus dou f by dou z into k. Dou f by dou x is 2x, so therefore 2xi. Dou f by dou y is 6yj plus 3z squared k. So you substitute the point 1, 1, 1 and you will get the gradient function as, or gradient field as 2i plus 6j plus 3k. What we want is a magnitude, so take the magnitude of this and it will be square root of 4 plus 36 plus 9, which is square root of 49, which is 7, corresponding to option A. Question number 4. the directional derivative of f of xy is equal to xy into x plus y by root 2 at 1 comma 1 in the direction of the unit vector at an angle of pi by 4 with the y-axis is given by. Now let's look at the concept of directional derivative. Directional derivative of f along A is del f dot A by the magnitude of A. This is a concept. So it's nothing but if f is a scalar field and P is a given point, we all know the surface normal represents the gradient, and here we have a certain vector A. The directional derivative of this scalar field along this direction is nothing but the projection of the gradient on this. So this projection is a directional derivative. Hence the formula appears like that. Now in this question, the vector A is a unit vector making an angle 45 degrees with the y-axis. So it also makes the same angle with the x-axis. So therefore, I plus j by root 2 will be the vector A. Okay, because cos alpha I plus sin alpha j. Because alpha is pi by 4, it will be 1 by root 2 in both the cases. So now let's look at the calculation. Vector A is now available, and then we have to find out the gradient of f. So we must comes from there. So start with f is equal to x square y plus xy square by root 2 and find out the gradient. The gradient will be dou f by dou x I plus dou f by dou y j. So you will get 2xy plus y squared I plus, with respect to y, you get x squared plus 2xy j by root 2. Now we are specifically calculating at 1 1. Therefore, at 1 1 del f will be 3i plus 3j by root 2. Now already the vector A is known, and you can see it's already a unit vector. Therefore, directional derivative is equal to del f dot A divided by magnitude of A. So take the dot product of this and this, because this is del f and that is A. So you will get 3 plus 3 by root 2 into root 2 is 2. 3i dot I is 3, 3j dot j is again 3, and then root 2 into root 2 is 2. So this will be 6 by 2, which is equal to 3, corresponding to option B. Question number 5. The function f of xy is equal to x square y minus 3xy plus 2y plus x has. There are 4 options given. No local extremum, 1 local minimum but no local maximum, 1 local maximum but no local minimum, and 1 local minimum and 1 local maximum. This question is based on function optimization, and let us go through the process quickly. First, get the partial derivatives. For function optimization, you work out first order and second order partial derivatives. Fx is dou f by dou x, which is 2xy minus 3y plus 1. Fy is x squared minus 3x plus 2. Fxx is 2y. Fxy is to differentiate fy with respect to x, and you'll get 2x minus 3, and fyy is 0. Now you get critical points. To get critical points, you solve these two equations. Fx is equal to 0, Fy is equal to 0. And from Fy is equal to 0, by solving this, you get x is equal to 1 or x is equal to 2. So when you substitute x is equal to 1, y is equal to 2 in Fx, you get the critical points. First case, you put x is equal to 1 in this and you will get 2y minus 3y plus 1 is equal to 0, giving y is equal to 1. So this gives the first critical point 1, 1. In the second case, when x is equal to 2, this gives 4y minus 3y plus 1 is equal to 0, giving y is equal to minus 1. So the second critical point is 2, minus 1. Now, we all know Hessian matrix has the structure so let us work out the Hessian matrix in both the cases. For this 1, 1 combination, fxx is 2, fxy is minus 1, again minus 1, fyy of course is 0. So when you find out the Hessian matrix character, this is indefinite. Why is it indefinite? Because this is positive, whereas this determinant is negative. So you know the rules are analysis of H is very important. I think I will just explain briefly what it means. Fxx, fyy minus fxy whole square positive and fxx positive makes it positive definite. And fxx, fyy minus fxy whole square greater than 0, fxx less than 0 makes it negative definite. Now if you look at this particular thing, fxx is positive fine, but if you take fxx, fyy, that is this into this, minus this product, makes that not positive. Therefore, it is indefinite. So this is a saddle point. Definitely not giving a maximum or minimum. Let us come to this case. H is equal to, again you substitute into this. Fxx will be 2y is minus 2 and then fxy, so you'll get 4 minus 3, 1, symmetrically 1 and this is 0. Again this is indefinite. That means this is also a saddle point. Which means neither the point 1, 1 nor 2, minus 1 gives a local maximum or minimum. So option 1 is correct because there are no extrema for this particular problem. So option A is correct for this problem. Question number 6. The point where the function f of xy is equal to x cube plus 3xy squared minus 15x squared minus 15y squared plus 72x has a local maximum is. This is a problem where again the optimization concept enters. So let's follow the due procedure. Get fx, fy, fxx, fxy, fyy. So we'll get 3x squared plus 3y squared minus 30x plus 72. Fy will give us 6xy minus 30y. Fxx will give us 6x minus 30. Fxy is 6y minus 30. And finally, fyy is again 6x minus 30. Fxy is the partial derivative of fy with respect to x or fx with respect to y. So you get that. In fact, we must be careful with fxy. We'll rework this one. Fy with respect to x will be just 6y, right? Now first let us solve these two and get the critical points. So solve fx is equal to 0, fy is equal to 0. Now when you take this fy is equal to 0, you will get 6y into x minus 5 is equal to 0. So you get y is equal to 0 or x is equal to 5. So two possibilities open out. One is when y is equal to 0 and the second case when x is equal to 5. So you substitute y is equal to 0 in fx. Similarly, you substitute x is equal to 5 in fx. So when you put y is equal to 0 in fx, you get 3x squared minus 30x plus 72 is equal to 0. Cancel out a 3. X squared minus 10x plus 24 is 0. So you get x is equal to 4 or x is equal to 6. So pair it up with y, you get 4 0 or 6 0. So two critical points from this case. Similarly, when you put x is equal to 5 in this, you will get y is equal to plus or minus 1. So you get 5 1 or 5 minus 1. So four critical points have to be analyzed. One by one, you substitute that into the Hessian matrix. fxx, fxy, fxy, fyy. And when you work out, suppose you take 4 comma 0, right? At 4 comma 0, let us analyze h. fxx will be 24 minus 30, that is minus 6. fxy will be 0. Then fyy is again minus 6. So please observe that fxx is negative and fxx fyy minus fxy whole squared will be minus 6 into minus 6, 36, minus 0 is 36, which is positive. This particular combination corresponds to a local maximum at 4 comma 0, and the correct option for this problem is A.